welcome to everyone. In the previous video, we have been discussing limits of metric spaces. Next, we will consider limits of metric spaces that comes as dilations of a fixed metric space. For example, if we have a metric space and we compress it more and more and more and more and more and more, and we have convergence, we will say that the limit is an asymptote of the space. It's an asymptotic space of the initial metric space. If instead we dilate more and more, we dilate, and we have convergent to something, then this limit will be called tangent or tangent space at that point of this metric space. What is interesting for our geometric viewpoint of in subRiemannian geometry is that Carnot groups appear both as asymptotic spaces of nilpotent groups, Riemannian nilpotent Lie groups, and also they appear as tangents of subRiemannian manifolds. Okay, so let's see the theory of dilating spaces and taking limits. We already said it in the previous video, but let's recall and make it more explicit what is the definition of a tangent space and of a asymptotic space. So here's the definition. Suppose you have two metric spaces, X and Y, metric spaces, and fix 2 points, X, little x in X, and little y in Y. Then, so first of all, we said that the metric space Y is a tangent space, or just a tangent of X at little x, if there exists a sequence lambda j going to infinity, such that the dilated metric space delta j x pointed at x converge Gromov-Hausdorff at the metric space y, little y. This is as j goes to infinity. Instead, we will say that the metric space yy is an asymptotic space. For x if there exists a sequence lambda j going to 0 such that these dilated spaces converge Gromov-Hausdorff to y as j goes to infinity. Okay, a little bit of remarks. So in both statements, I put the indefinite article A, because it could be a priori that for different sequences going to infinity, we might have different tangents. Okay, and remember, a priori, we might not even have any tangent. It could be that for all sequences, for sequence lambda j, the sequence of metric space might not converge. But even if they converge, they might not converge always to one object. The same thing for the asymptotic spaces. The limit might depend on the sequence. It is easy to see that when instead there is only one possible limit, we have only one tangent and one asymptotic space, then the asymptotic space is going to be dilation invariant. And therefore, in that case, one uses the terms tangent cone and asymptotic cone. Okay, but for now we just use the term space. Okay, now another comment is in the case of tangent, it's pretty clear that this sequence will depend on the choice of base point, okay? Because it's like a function, taking the derivative at a point, it might be different than taking the derivative at another point. But in the asymptotic spaces, also in the terminology, I didn't specify that this was at x. And the reason is that if you have convergence for one x, you really have convergence for any other x prime. Let me write this as an exercise for you. It's very simple, right? So if you have some lambda j going to 0 and lambda jx x converges Gromov-Hausdorff to yy. In other words, if yy is an asymptotic cone, asymptotic space, then the same sequence based at another point x prime converges to the same exact pointed metric space. Gromov-Hausdorff. This is for all x prime in x. Okay, so from this we get the notion of asymptotic space is independent from the fixed base point. Okay, this was a comment. Let's see some examples. Okay, first let's start with a basic example. Let's say we have a bounded metric space. Then what happens is that when we dilate the metric space, then really the diameter is dilated by exactly the same factor. This is very easy to check. So what happens is that if we take some numbers, let's call them epsilon, that are going to 0, right? Then this metric space, as epsilon goes to 0, this will converge to just a single point metric space as epsilon goes to 0, right? Because as we said, that if you have a sequence of metric space whose diameter is going to 0, then they converge to a point in the metric space formed by a point, right? And this will, so what we clarify is this obvious, really expected result that the asymptotic, now we will call it cone, of a bounded metric space is a point. And this is, we are formalizing something that is geometrically quite clear. So you have a metric space that has bounded diameter, right? So think of, so it's bounded. And now what you're going to do, you're going to shrink it, right? So you're taking a number very small, and then you're dilating the distance. So if, for example, if before the distance was at maximum 1, then when you multiply by epsilon, the distance is at most 1 epsilon. You should think of something shrinking. And the limit, of course, is going to be just a single point. Okay, so this is for the intuition. Now, let's make something a little bit more advanced now. So let's give example 2. Okay, so let's consider Zn inside Rn. So this is like the grid, or like the points with integer. I'm going to take the picture in R2, right? So this is the points with integer coordinates. Okay, let's fix a distance. Which distance? Now, of course, we have kind of two canonical or standard choices. We can just take, the Euclidean distance and restrict it to the n, or we can also take the distance given by the grid. Of course, the distance given by the grid, this is nothing else than the L1 distance on the plane restricted to the n. So let's be general and let's say that just fix any norm, fix a norm, let's call it norm, on Rn and restrict it. So, and then this norm will give a distance, and then we restrict the distance function on Zn. Okay. Now, So what we will have is that if we now multiply Zn by epsilon as a metric space, so think this is a metric space, we multiply by epsilon. This is really the same of saying, take the points as that have coordinate an integer multiple of epsilon with always the same distance, d, restricted to epsilon Zn. Okay, so again, if the distance was, so the one norm where these edges were distance 1, then if we take, let's say, so this was Zn, Z2, 1/2 Z2 is the metric space. Now you take points where this distance is 1/2. This distance is 1/2. Okay, so it's quite clear that now what we have, that this epsilon Zn is Gromov-Hausdorff converging to, as epsilon goes to 0, to Rn, and then equipped with the distance d associated to the norm. Associated to the norm. So in other words, what we have proved that the asymptotic cone of Zn with restricted distance is Rn with that distance. Again, I hope that what we proved was geometrically very intuitive, right? So we start with this grid, and then we were doing a grid that was much finer. And then what we are saying is that since when this grid becomes finer and finer, we get the whole plane or the whole Rn. Okay, now we have agreed on this. Let's generalize this result. A generalization. So let's say G is a Carnot group. Of course, with the Carnot-Carathéodory distance d and dilation delta lambda, factor lambda. And now let's take a subset of G that is a net in G. Okay, what does mean it's a net? Means that for some constant, let's say some exist R, such that if you take the neighborhood, so the union of all the balls on lambda with radius R, then this is all of G. Okay? So every point of G is at distance less than R from a point in gamma. Just for simplicity, I think that really like 1 is in the in gamma, because we want to think of a pointed metric space. Okay. Now, so what we do on gamma, we restrict the distance function d. Okay, my claim now is that if we dilate by epsilon this subset, as epsilon goes to 0, the sequence of metric spaces will converge to the Carnot group. As epsilon going to 0, right? So, and this is a generalization of the example before, because we were taking Zn inside Rn. Okay, let's clarify why this is true. Okay. So to prove this, one has to find Hausdorff approximation from this sequence of metric spaces. Okay, already take any sequence of epsilon j going to 0, and we have to prove that they converge to G. Okay, so I will really give a Gromov-Hausdorff approximation for every epsilon to the space G. Okay, what is the map? So for all epsilon, the map phi epsilon from gamma to G okay, maybe one should pay attention. Okay, remember that this space here is the same of the dilated space by lambda. So maybe let's write here. Let's write epsilon times gamma. So as a set is gamma, with a different metric. Okay, so on the set gamma, I will define phi epsilon of a point gamma as delta epsilon of gamma. Now what we have, as we proved before in the previous video, so now this map here, gamma 1, this map becomes an isometry between epsilon lambda and the image of lambda. So this is equal to, so by definition, it is delta epsilon gamma 1, delta epsilon gamma 2. By the property of the distance, this is delta of the dilation gamma 1, gamma 2. So this can be seen an isometry between lambda with the distance epsilon d, namely in the space epsilon lambda, and the space on the image G. Okay? So in other words, phi epsilon is an isometric embedding namely a 1-0 quasi-isometry of lambda epsilon d, which is what we call epsilon lambda, and or into G with this distance d. Let's see that this is almost surjective, moreover. So what is the image of lambda? So I claim that if we take now the epsilon R neighborhood, we obtain everything. Neighborhood, we obtain everything. Okay, let's check. So this is delta epsilon lambda, epsilon R. And here we are taking the distance in G, okay? So, okay. So now because of the dilation, this is exactly epsilon times the ball lambda at gamma with radius R. And we know this by assumption that this was G. Okay? Or maybe this is delta epsilon. And this is delta epsilon G, which is G. So what we have understood is that phi epsilon is an epsilon R, is epsilon is quasi-surjective, okay? Was an 1-0 quasi-isometry. So in total, epsilon, phi epsilon is an 1 comma epsilon R quasi-isometry. And therefore, by one of the criterion that we discussed in the previous video, the sequence converge to G. In other words, the asymptotic cone of gamma is G. All right. And also, as said in the previous video, one can apply this. We did already this calculation when gamma was all of G. And this will rephrase the fact that for each cardinal group G, there is one asymptotic space isometric isometric to G. Let's call it asymptotic cone because it's always really it converges for all epsilon. And likewise, we also have a tangent because again, if we dilate as epsilon goes to infinity, also we have a sequence equal to G and a tangent cone at every point, isometric to G. Okay, so Carnot groups are the tangents and the asymptotic cones of themselves. Now let's see a different kind of example where you might have more than one asymptotic space. Okay, and you can also think of examples where you don't have asymptotic spaces. Okay, so here's an example where the asymptotic spaces might not be unique. Okay, I will present the metric space with a picture. Okay, you can write formulas, but I think the picture is much more clear when we want to then dilate. So, picture. So it's like this. So, okay, we are in R2. So the example starts like this. Okay, take a horizontal segment from 0. So this is a horizontal segment. Then you take a longer vertical segment. Then you continue and you take an even longer horizontal segment. Then you take a much longer and so on. So there is this zigzag, and every time is a longer longer segment. Now, what happens is that when you shrink, when you are multiplying by an epsilon that is very small, what you could do, you can like up to a point, you can shrink it to be in a very small neighborhood of the identity, and then you have a segment. So you have a segment that is very long. So what you are going to have is something that is something near the origin, very long segment, and then something outside a big ball. But now if you shrink differently, like if you shrink all this, if you shrink all this part, then you're going to have something small, then a long segment here will give something like this, and so on. So you should agree that then what you're going to have is that you can have this half line as an asymptotic cone, but also this other half line as an asymptotic cone for different sequences, of course. Then R plus times 0 is an asymptotic cone, asymptotic space, and also 0 times R plus is an asymptotic space. Actually, you can think and you can see that there are even more than just 2 examples. So there are more asymptotic space in this example. Okay, so don't think that asymptotic space should be unique in general, okay? And Again, think of also examples where you don't have really any convergence. Okay. This was a discussion about asymptotic spaces. Now, let's discuss a little bit about tangent spaces. Let's start also with an example. Example of tangents. Now, let's make it very simple. Let's consider the sphere so as n-1 sphere in Rn. Okay, maybe let's make it even more simple. Just say S1 inside R2. Okay, what is the width distance? Let's say with either the path distance or the arc, a chordal. Let's call chordal distance, namely from. Okay, let's make a picture. Okay, so let's say you have a circle, and then between 2 points, you can take the straight line, so this, and measure the distance, or you can take the arc following. So these two distances, of course, are different. But if we won't take the tangent at this point, you will see that actually these distances are very, very close. They get close to each other, so that the tangent is going to be the same. Okay. So let's try to. The terminology is also to blow up, right? So we are going to dilate the space centered at this point. Okay. So maybe let me take the sphere, or the circle in this case, centered at this point, say that this is 0. Okay, so let's write an equation. Oh, so take so S1 to be now the points x, y, such that, okay, I want 0 here. So it's x squared plus 1 minus of plus, yes, minus 1 square equal to 1. Let me check if it's correct, right? Because so also this is 0, 2 should also be okay. Yes. Yeah. Okay. So this is the equation for the picture that I gave, right? So these are the axes. All right. So now we can dilate. And again, since we are inside the Carnot group, like R2, instead of dilating the metric, we can dilate with the dilation the set. Okay. So then lambda S1, let's just call it S, as a metric space is the same as lambda S as subset of R2. Namely, if you consider the distance on S and dilate the distance by lambda, it's the same as saying dilate the points on S to be other points on R2 and just restrict the distance on R2. Okay. So now the claim is what we actually expect is that as lambda goes to infinity, then this sequence delta S converges to this line here, which is R times 0, which as a metric space is the same as R. So we will therefore have that the tangent of S at 0 is R. And this is good. I mean, this is our intuition, because dilating by a factor that is going to infinity means that we are dilating this the circle and make it bigger and bigger, and then in the limit we'll just have the line. Okay, let's also build. So let's try to understand why this is true. Okay, so let's really parameterize this this space, and also consider that if I want to consider the tangent at this point, right, of S, it's enough to just take a neighborhood of 0 in S and blow up this neighborhood, right? Because I mean, this is going to be at further distance than this neighborhood, right? So let me write it. So indeed, to take the tangent at p equals 0, 0, 0, it's enough to consider and blow up a neighborhood of P. So let's take the lower part of the circle. So sigma to be all those points x, should I put here? So let me calculate. So it was x squared plus 1 minus y minus 1 squared equal to 1, which means that, okay, 1 minus 1 is equal to plus or minus square root of 1 minus x squared. So which one should I take? So I wonder when x is equal to 0, when x is equal to 0, y should be also equal to 0. So I should put, so this on the other side becomes plus 1. So it has to be 0. I should take minus. Okay. So let's see if you agree with me. The function is, the graphing function is 1 minus square root of 1 minus x squared, where x is from minus 1 and 1. Okay, so this was to parameterize just this part here of the circle. Okay, now let's take let's dilate the space. Lambda sigma is equal to, dilate the points, lambda x lambda minus, or maybe let's write it with parentheses, 1 minus square root of 1 minus x squared x in minus 1, 1. So let's change, let's call lambda x equal to t. What we are going to have is t lambda 1 minus square root of 1 minus t square over lambda square, such that t now is in minus lambda lambda. Now, as you see, the domain of definition is getting bigger and bigger, and the limit is going to be the all real line. Okay, so this, all of these are functions. So this is the graph of the function. So what's happening to this graph? Okay, let me calculate it. So what is this limit? Lambda. Okay, I'm going to make something very elementary. Calculating the limit of this map as lambda is going to infinity. Okay, so let me probably multiply by 1 plus square root 1 minus t square lambda square 1 plus square root of 1 minus t square lambda square. So this is going to be lambda difference of squares, so 1 minus t square lambda square divided by 1 plus square root of 1 minus t square lambda square. Now, so 1 minus 1 is 0, then this lambda cancels with this lambda, and we are going to have, so the minus becomes a plus, so it's going to be t squared divided by lambda divided by 1 plus square root of 1 minus t squared lambda squared. Okay, so now what happens? Okay, this ratio is going to go, so lambda is going to infinity, so this is going to go to 0. This is also going to 0, and this is going to be 1 plus 1. This is going to go to 2. 1 over 2. So this limit here is going to 0. Okay, so maybe let's write it. So this limit here goes to 0 as lambda goes to infinity. So this will tell us that the metric space, at least the graphs, are converging to the graph of the zero function, which is this space here. Okay, so maybe this was just a discussion about graphs of functions, but let's see it as really metric space. So really check that the maps phi lambda from lambda sigma to R cross 0, which are just the projection on the first factor of this restricted to lambda sigma. So pi 1 of x, y is equal to x0. This is the map. I claim that these maps, or sequence of maps in lambda, form as lambda goes to infinity, a Hausdorff approximating sequence. Okay. Therefore, we prove that the tangent of a circle are lines. Of course, this was not really surprising at all, I hope. And similarly, one can prove that if you take any Riemannian manifold of dimension n, the tangent is Rn. Okay? Now, this last statement has a generalization in the case of subRiemannian manifolds. And this is something we will discuss. So I finish with just stating two deep results that we will discuss in the next videos. Maybe we will not really give the whole proofs because they're quite deep and also long in proof. So the first is what I was telling you about tangents of subRiemannian manifolds. So it was proved by Mitchell, but then Bellaiche give a more correct proof. So suppose you have an equiregular subRiemannian manifold, and you fix a point in M, then there exists G Carnot group such that M has G as only tangent at P. So all sequences, all dilations going to infinity will make P M dilated with these factors pointed at P converge to G. Okay. Remember, G is a group, so it's homogeneous. It's not important where you point it. Okay, so this was regarding tangents. And going back to asymptotic cones, then I will discuss a theorem of Pansu, the same Pansu that proved the Rademacher theorem for Carnot groups, that if you have n a Riemannian nilpotent Lie group, so a Lie group that is nilpotent and equipped a left invariant Riemannian metric, then there exists a Carnot group, G Carnot group, such that N has an asymptotic cone, and this asymptotic cone is G has only asymptotic space. Okay, so we will say more about these two results in the future. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below.